In this video, we state and prove Wilson's theorem. Wilson's theorem states if p is a prime number, then factorial p minus 1 is congruent to minus 1 mod p, or factorial p minus 1 plus 1 is divisible by p, or the prime. You see that factorial p minus 1 is the product of 1 and 2 and 3 and 4 and so on up to p minus 1. That's a big product and difficult to handle, right? Let's look at a particular case, p equal to 7. So when we choose p equal to 7, p minus 1 is 6. So we should get factorial 6 is congruent to minus 1 mod 7. We are choosing p equal to 7. Is that true? That is true if factorial 6 is definitely the product of 1 and 2 and 3 and 4 and 5 and 6. This product is congruent to minus 1 mod 7. Again, is that true? Okay, yes, it is definitely true. But of course, it follows by Wilson's theorem. But let's do it. Observe that the product of 2 and 4, that's simply congruent to 1 mod 7. 2 times 4 is 8. 8 is congruent to 1 mod 7. Nice. How about 3 and 5? The product of 3 and 5 is 15. And 15 is again congruent to 1 mod 7. The product of 3 and 5 is congruent to 1 mod 7. What is left out? 1 and 6. Product of 1 and 6 is congruent to minus 1 mod 7. 1 and 6, this product is congruent to minus 1 mod 7. Okay, we got 3 congruences. 1, 2, 3. Let's multiply those out. So multiplying, we find that 2 times 4 times 3 times 5 times 1 times 6, that product is congruent to minus 1 mod 7. But how much is that product? You see that 1, 2, 3, 4, 5, 6 all occur. So that's definitely equal to factorial 6. So factorial 6 is congruent to minus 1 mod 7. Nice. So we could show that the Wilson's theorem is true for p equal to 7, for that prime p equal to 7. Further, we observe that we are simply choosing two integers 2, 4, 3, 5, 1, 6, and they turns out to be different, and when we multiply those out we get factorial 6. So let's choose an integer a1, comma a1 is greater than or equal to 1 and less than or equal to p minus 1. So we begin the general proof now. A1 is greater than or equal to 1 and less than or equal to p minus 1. Now we just need to another pair. Then the congruence, so the proof begins here, then the congruence a1x is congruent to 1 mod p poses unique solution modulo p. Poses unique solution modulo the prime. Why should it? Because a1 is greater than or equal to 1 and less than or equal to p minus 1. So GCD of a1 comma p is equal to 1. a1 and p do not have anything in common, any prime factor in common. If they are relatively prime, then by the theory of congruences, this equation a1x is congruent to 1 mod p poses unique solution modulo p. When we say modulo p, that imply that we can restrict x greater than or equal to 1, less than or equal to p. But x cannot be equal to p because left hand side will be congruent to 0 mod p and right hand side 1. So we can say that x is greater than or equal to 1, less than or equal to p minus 1. Further, if we look at our example, we are getting different number 2, 4, 3, 5, 1, 6. They are all different. Let's see when does it happen that a1 and x are different. So instead of saying when does it happen that a1 and x are different, let's ask this question, when does it happen that a1 and x are same? If a1 is equal to x, then x times x, we can simply write x instead of a1, so x times x is x square, turns out to be congruent to 1 mod p. See, x square is congruent to 1 mod p, that is same as saying x square minus 1 is congruent to 0 mod p. Wow, x square minus 1 is simply x square minus 1 square. We know how to factorize a square minus b square and say that x minus 1 and x plus 1, this product is congruent to 0 mod p. Or the product x minus 1 times x plus 1 is a multiple of prime. Now if the product is divisible by prime, then one of the number has to be divisible by prime. So x minus 1 is congruent to 0 mod p, or x plus 1 is congruent to 0 mod p. From here we can say that x is congruent to 1 mod p, or x is congruent to minus 1 mod p. We can combine this up and say that x is congruent to plus minus 1 mod p. But we are restricting x from 1 to p minus 1. So x can be 1 or p minus 1. So if we want that a1 is different from x, then it's sufficient to show that a1 and x are different from 1 and p minus 1. So we assume a1 is not equal to 1, comma, a1 is not equal to p minus 1. But a1 is changing from 1 to p minus 1. So a1 is greater than or equal to 2, less than or equal to p minus 2. What about x? X is a solution of the congruence a1x is congruent to 1 mod p. If a1 is equal to 1, then we get x equal to 1. If a1 equal to p minus 1, then we get x equal to p minus 1. The other way is also true. If x equal to 1, then we get a1 equal to 1. If x equal to p minus 1, then a1 is also equal to p minus 1, because they are all lying between 1 and p minus 1. So x will also be greater than or equal to 2, less than or equal to p minus 2. Once again, the congruence a1x is congruent to 1 possesses a unique solution modulo p. a1 is greater than or equal to 2 and less than or equal to p minus 2, and x also turns out to be greater than or equal to 2, less than or equal to p minus 2. How many numbers are there from 2 to p minus 2? Let's write 1, 2, 3 and so on up to p minus 2. If I write it out, there are p minus 2 numbers. But if I remove 1, then there are p minus 3 numbers. The congruence poses unique solution. So we can say A1 prime is congruent to 1 mod P for some A1 prime greater than or equal to 2, less than or equal to P minus 2. Oh, we got some problem. Observe that we are saying A1 greater than or equal to 2, less than or equal to P minus 2. What if P equal to 2? Or what if P equal to 3? No such A1 can be found. So remember, we are leaving some gap in the proof initially. If P equal to 2 or 3, comma, then factorial P minus 1 plus 1 equal to, when I choose P equal to 2, then 2 minus 1 is 1 factorial plus 1, that's equal to 2. 3 minus 1 factorial is 2, 2 plus 1 is 3. So factorial P minus 1 is congruent to minus 1 mod 2, comma, factorial P minus 1 is congruent to minus 1 mod 3. So we assume P greater than or equal to 5. Okay, proof continues. Now if I choose P equal to 5, 5 minus 2 is 3, A1 and A1 prime, there are just two choices, 2 and 3, these are the only choices. So this will be the only case. We won't be able to find another positive integer. If P equal to 5, then we are simply done. Then we are done. We can simply verify it, or we got one pair and that's what we need. We are done. So we assume P greater than or equal to 7. If P is greater than or equal to 7, comma, then we can choose A2 different from A1 and A1 prime. And so we will be able to solve this congruence and say that A2 prime, which is congruent to 1 mod P. There exists A2 prime for some A2 prime greater than or equal to 2, less than or equal to P minus 2. How long can we continue? See that A1, A2, they are all greater than or equal to 2, less than or equal to P minus 2. So we cannot continue for long. Continuing, A3 prime is congruent to 1 mod P, and so on. We got P minus 3 numbers of A1. A P minus 3 by 2 times A P minus 3 by 2 prime is congruent to 1 mod P. In total, how many integers did we choose? 1, 2, 3, 4 and so on. We got P p minus 3 number of integers, and they are all greater than or equal to 2 and less than or equal to p minus 2. So we simply multiply. We did start with a1 prime, which is congruent to 1. a1 prime, then a2 prime, and so on, ap minus 3 by 2, ap minus 3 by 2 prime. The product is congruent to 1 mod p. But they are all the integers from 2 to p minus 2. So we can say that factorial p minus 2 is congruent to 1 mod p. But further we know that p minus 1 is congruent to minus 1 mod p. If we multiply those out, if we multiply factorial p minus 2 with p minus 1, we get factorial p minus 1 is congruent to minus 1 mod p. So indeed we proved Wilson's theorem.